Hey everybody, this is a continuation video in regards to a series parallel resistive circuit. In the previous video, I took the circuit that I have drawn here and solved for resistance total utilizing this reduced series circuit. So I have made this video to show you how to further solve this circuit using Kirchoff's current and voltage law. To begin, I would like to solve for the individual volt drops that would be found across the reduced series circuit. To do that, I want to solve the current that's flowing through the circuit. We would do so using Ohm's law. So current total equals supply voltage divided by resistance total. The resistance total would be the sum of the three resistors that we have reduced into a series circuit. So source voltage is given 120 volts. Divide that by the resistance total, which we worked out to be 20.44 ohms. Resistors in series are simply additive, and that constitutes in a current value of 5.871 amps flowing. That will be the value of current that is flowing in our reduced series circuit, as well as the value of current that will be flowing in our original drawing, 5.871 amps. So the first rule I want to apply to this series parallel circuit is Kirchoff's voltage law, and it simply states that the sum of the volt drops will equal the applied voltage. Then we will take the individual volt drops that we've solved using Ohm's law and convert them back to the original circuit, and then further solve the currents that's flowing through the branches. So we want to figure out what the volt drop is going to be across resistor 1. The volt drop is going to be across resistor Rx. Rx consists of branches R2 and 3 reduced with R4 and 5. R2 and 3, 4, and 5 are directly in parallel. And resistor R6-7 is a reduction of R6 and R7, reduced, again, being directly in parallel. So the volt drop that would be found across the first resistor would be found using Ohm's law. So VR1 equals IR1 times R1. Current is, as solved, 5.871 amps times the resistance of resistor 1, 10 ohms, and that would give us a volt drop of 58.71 volts. So if I were to put my voltmeter across the first resistor, I would get a voltage reading of 58.71 volts across, meaning parallel. Okay, so I'm going to continue using Ohm's law to solve for the rest of the volt drops. So VRX, volt drop across resistor X, equals IRX times RX. The current flowing through resistor RX is the same as what's flowing through resistor 1, a series circuit. So 5.871 amps times the resistance of resistor X, which is 6 ohms, and that would give us a volt drop reading of 35.226 volts. If I were to put my voltmeter across resistor Rx, I would read 35.22 volts. And the last resistor, VR67, equals IR67 times R67, again current, series circuit, 5.871 amps, times the resistance value, 4.44 ohms. That would give us a volt drop of 26.067 volts. If I were to put my voltmeter across resistor R6, I would read 26.067 volts. So using Ohm's law, we have proven that Kirchoff's voltage law for a series parallel circuit is in fact true. So if we were to take 58.71 volts, add that to the volt drop across Rx, so 35.22 volts, plus the volt drop across resistor R67, we would come up with our supply voltage of 120 volts. The next step to solving all the variables of the series parallel circuit will be to take these individual volt drops and place them appropriately in the original circuit. Okay, so now I've taken the volt drops that we had solved and placed them in their appropriate positions in our series parallel resistive circuit. Now I want to use Kirchoff's current law to solve for the unknown variables, meaning the value of current that's flowing through the individual branches. So Kirchoff's current law in a series parallel states that the sum of the current, you will not lose or gain current in the circuit. So if I have a 5.871 current total, I will not exceed that value of current through the individual branches. Being that resistor 1 is in series with everything else in the circuit, I can already safely say that IR1 equals I total, 5.871 amps. That 5.871 amps comes to this point here and then splits proportionally to the volt drop and the value of resistance that is in the particular loads. So I want to figure out how much current is flowing through resistor 2, 3, as well as how much current is flowing through resistor 4 and 5. I cannot just take the 5.87 divided by 2 because the values of resistance total in those branches are not the same. So I want to figure out how much current is flowing through resistor 2, 3. So I have put down that there are 35.26 volts across these 2 points. That would be true across these 2 points also because electrically they are of the same point. So resistor 2, 3 added together, R2 and R3 are directly in series, would be directly proportionally, directly parallel to resistor 4 and 5 added together, therefore meaning they would share the same value of volt drop. So the current that's flowing through resistor 2, 3 would be VR23, so the volt drop across resistor 2, 3 divided by the resistance value of 2, 3. So 35.226 is the value of voltage divided by the resistance. Again, 2 and 3 are directly in series, so that would give me 15 ohms of resistance. Okay, and that would give me 2.35 amps of current flowing. So if Kirchoff's current law is true, I can roughly estimate the value of current expected to flow through resistors 4 and 5 by taking my I total, subtracting my 2.35. I have an expected current draw of around 3.5. So I want to prove that that's true by using Ohm's law. So IR45 equals the volt drop of 4.5 divided by the resistance value of 4.5. The voltage that is across resistor 4 and 5 is the same as the previous formula, so 35.226 volts. They are directly in parallel with each other, so they share that value of volt drop, divided by the resistance value. R4 and R5 are directly in series with each other, so I would just add those resistances together, and that would give me 10 ohms. That indicates that I have a value of 3.5226 or 3 amps flowing through the bottom branch here. And that is proving that Kirchoff's current law is true. You do not lose or gain current in a series parallel resistive circuit, as our branches are additive to our resistance total. Now we're going to have that value of current come back together completely here and then disperse proportionally through resistors 6 and 7. I want to figure out how much current is flowing through the individual branches. So IR6 equals the volt drop across resistor 6 divided by the resistance of that 6th resistor. The volt drop, according to our drawing here, is 26.067 volts divided by 8 ohms, which equals 3.26 amps. Okay, so I have 3.26 amps. Again, we're proving that Kirchoff's current law for a series parallel circuit is true, so I could take that 5.87 amps, subtract 3.26, and get an expected current draw for resistor 7. I'm expecting to have around 2.6 amps of current flowing through the resistor, which looks proportionate to the numbers that we have. IR7 equals VR7 divided by R7. So the volt drop across R6 is consistent with the volt drop across R7 because they are directly in parallel with each other rather. So 26.067 volts. Divide that by 10 ohms, and that gives us 2.61 amps. So we have effectively proven that Kirchoff's voltage law and current law are applicable and do work in a series parallel circuit. Thank you.